Welcome to the lecture series of network theory. In our last class, we have already started learning about the application of Thevenin's theorem. And in the last class, we solved a few numericals, and to simplify them, we applied Thevenin's theorem for DC circuits and for independent sources. In today's class, we will be applying Thevenin's theorem for DC circuits having dependent sources along with independent sources. We already know that Thevenin's theorem is one of the most important theorems in circuit theory, and we already have the concept of dependent sources because I have already taken a class on that. So let's get started. If we go by the statement of the Thevenin's theorem, it is same as we have discussed in the last class. So that two-terminal linear bilateral DC network will be replaced by an equivalent circuit where that circuit will have a voltage source VTH and a resistor RTH which will be connected in series. Now this VTH and RTH have the same meaning. So here RTH will be the equivalent or internal resistance of the network when we look from the concerned or output terminals with all the energy sources deactivated. Now we already understand that what is this deactivation of energy sources mean, and VTH will be the open circuit voltage across those concerned terminals. Now if we look at the circuit, here in this circuit we have three resistors and we have one independent voltage source and we have here one dependent source. Now this dependent source can be one of the four types that I have already discussed in one of my previous lectures. Now if we Thevenize this net electrical network, in the final circuit we will have an equivalent voltage source VTH, which will be again the open circuit voltage across those concerned terminals, and then with that we will have a resistor connected in series, and that resistor will be called as Thevenin equivalent resistance, and that is the internal resistance of that network. And then finally with that circuit we will reconnect the load resistor RL that we have removed, or through which the current or voltage we want to find out. Now finally again the current value will be nothing but VTH divided by RTH plus RL. Now to find out this VTH and RTH value for an electrical network where we have dependent sources, this time it will be a bit different. So I will next discuss that approach in step-by-step manner, and then we will solve a few numericals on that. So here again we have a DC network where we have one independent source and one dependent source and three resistors. So in the first case what we will do, we will remove the concerned resistor through which suppose we want to find out the current value. So this RL is our concerned resistor which is connected between these two terminals AB. So in the first step we will remove that load or concerned resistor. So when we will remove that resistor, it will create open terminals like this, and in the second step we will find out the voltage drop across those two terminals. So this will be open circuit voltage across these two terminals AB, and that open circuit voltage VOC will be our Thevenin's equivalent voltage for the whole network. So this is what we do in the second step. Now in the next step what we will do is, this time we will short these two terminals AB, and we will keep the dependent source, we will keep the independent sources, how many we have in that circuit, and after sorting this path, these two terminals AB, we will find out the short circuit current which is flowing through this path. So as per this circuit, the current which is flowing through this shorted path which is between these two terminals AB, this is the current what we can say that which is flowing through this resistor R. So whatever current will be flowing through this resistor R2, that means that current will be flowing through this path between AB terminals. Now after finding out this current value ISC, what we will do, we will take the ratio of the VOC that we have found out in step 2 and the ISC what we have found out in step 3. So this ratio will be the measurement of the Thevenin's equivalent resistance this time. Now after finding out the VOC or VTH and RTH, we will draw the simplified circuit which will have the VTH and RTH in series, and with that we will reconnect the load resistor RL, and we can easily find out the current value, which will be this VTH divided by RTH plus RL. So this time what we have done is, here after finding out the VOC, we have shorted those two terminals and we have found out the short circuit current through that path, and we have divided that VOC by ISC, the short circuit current, and that way we have found out the Thevenin's equivalent resistance, which is the internal resistance of that circuit. So this is one of the methods that we apply in that electrical network to simplify that by applying Thevenin's theorem when we have dependent sources also along with independent sources. Now we have another method that we can apply to simplify that circuit by applying Thevenin's theorem. Now in this method, what we do is, as we can see in this electrical circuit, we have again three resistors. We have one independent voltage source and one dependent source here, and this could be again any of the four types that we know. So in the first step, what we will do, we will again remove this load resistor or concerned resistor across these two terminals AB, and then in the next step, as we can see here, it will create open terminals here. So as we have done previously, the same way we will find out the open circuit voltage here, and that will be again the measurement of Thevenin's equivalent voltage. Now in the next step, what we will do is we will connect a DC voltage source between these two open terminals. Let's say that the voltage value of that DC independent voltage source is VDC, and that is supplying some current, DC current IDC, in that circuit. And along with that, what more we will do is we will deactivate all other independent sources from that circuit. So we'll simply sort that path where that voltage source was connected, and this voltage source was ideal source. So here, otherwise, if it is not an ideal voltage source, we will keep the resistance value. And we also know how to deactivate the current source. So this time we will connect a DC voltage source between those open terminals, and we will deactivate all other independent voltage and current sources, but we will keep the dependent source there. Now this voltage source will supply this current IDC, and finally from that circuit we will find out the ratio of that DC voltage VDC and DC current IDC, and that will be the measurement of Thevenin's equivalent resistance. And after finding out that RTH, what we will do is, in the final step, we will connect that VTH that we have found out the way we have done in previous cases also, for the circuits where we have only independent sources, and for the circuit where we have dependent source along with independent source, by using the first method that we have learned in this class itself. And after finding out VOC, we will find out RTH. This time it will be the ratio of VDC and IDC. VDC is the voltage source that we have connected between those open two terminals, and IDC is that DC current which is supplied by this DC voltage source. Now after reconnecting this RL between these two terminals, same way we will find out the current value, and this is again VTH divided by RTH plus RL. So this is the second method how we can find out the current value through the concerned resistor. Next we will solve a few numericals based on these two methods. Now in this circuit, what we can see here, that we have three resistors. We have one independent voltage source and one dependent voltage source. And how this dependent voltage source depends, this depends on the current value which is flowing through this 2 ohm resistor. Value of this voltage source is 2I. Now we have to Thevenize this circuit where we have dependent source, and we have to find out the current value through 4 ohm resistor. That means this resistor. So in the first step, what we will do is, let's say these are the terminals A and B. So we will remove this 4 ohm resistor, and that will create open terminals here, and across which we will find out the open circuit voltage. And to find out that, what we will do here is, as we can see, after removing this 4 ohm resistor, this through this 2 ohm resistor no current will be flowing. That means the VOC will be simply the measurement of the voltage which will be dropped across these two terminals. So that means the measurement of 2I1. So if we can simplify this part of the circuit and if we can find out the value of I1, so that will give us the voltage drop across these two terminals AB, that means the measurement of VOC. Now to simplify or to find out the value of I1, what we can do is, as we can see here in this part of the circuit, these three components are connected in series and they form a closed path or loop. So easily we can apply the concept of KVL here. Now if we apply the concept of KVL here, the equation that we will be getting is, if we suppose start traversing from this point, then from negative to positive terminal, when we are traversing, if that value we take as negative, then it will be minus 10, then plus 2I1, this voltage drop, and then the voltage value which is again 2I1. So this time again we are traversing from positive terminal to negative terminal, so it will be 2I1 and that will be equal to 0. So it will be 4I1 which will be equal to 10. That means I1 will be equal to 2.5 ampere. So the voltage drop across these two terminals AB will be 2 multiplied by 2.5, which measures 5 volts. So the VOC or VTH for this circuit will be 5 volt. Next we will find out the equivalent resistance of this network, that means Thevenin's equivalent resistance. And to do that, if we use the first method, then what we have to do is, as per that method, we short those terminals, open terminal, and then we find out the current value or short circuit current value which flows through that path. Now if we look at this circuit, we can see here that the if the current value is ISC here, then the voltage drop across this 2 ohm resistor will be simply 2 multiplied by ISC, that means 2IS, and this voltage drop across this 2 ohm resistor will be nothing but the voltage drop that we'll be getting between these 2 points C and D, because this resistor and this voltage source, they are connected in parallel. So if we can find out the voltage value of this voltage drop, then that will be the voltage drop across this 2 ohm resistor, and easily we can find out the value of IS. So the voltage value across voltage value of this voltage source is 2I2, as we can see in this circuit, and this time it is I2 because in the original circuit the current that was flowing through this 2 ohm resistor, that was taken or assumed as I, and that was the current which has the combined effect of this independent source and dependent source, and we also had this resistor. But in the previous case, since we removed that resistor, so that's why the current value through this 2 ohm resistor will be changed, and that's why instead of I we took I1. And in this case, again, since we are shorting this path, so this time also the current value will not be same as, or may not be same as I or I1. So this time also I have taken a separate value which is represented by I. So voltage value of this voltage source will be accordingly 2I. Now 2I2, we can say that 2ISC, this voltage drop will be equal to 2I2, the voltage value of that voltage source. So this two value, if we equate these two values, then we can say that ISC will be equal to I2. That means the current which is flowing through this resistor will be equal to the current value through this shorted path. So if we can find out this value, that will be helpful for us. Now if we analyze this part of the circuit, and again we can see here that these three components have formed a closed loop. So if we apply KVL here, then we can easily find out the value of I2. So if we apply KVL here, then the equation that we'll be getting again minus 10 plus 2I2 plus 2I2, and that will be equal to 0. So if we simplify this equation, it will be simply 10 by 4. So this time again 2.5 ampere. That means the voltage drop or voltage value of that dependent voltage source will be 2I2, that means 5 volt. So RTH value will be, as per the first method that we know, this will be simply VOC divided by ISC, and VOC value we have found out as, we have obtained as 5 volt. So this will be 5, and ISC value will be this 2.5 ampere, that means 2 ohm. Now if we redraw the circuit, then it will look like this will be VTH, which has value 5 volt. Then we in series we will have the RTH, which has value 2 ohm, and then we will reconnect the load resistor, which has the value 4 ohm. This is also 4. So I will be simply 5 volt divided by 2 plus 4. So it will be 5 by 6. That means it will give us 0.833 ampere. So the current value through this 4 ohm resistor will be 0.833 ampere, and this is the way how we can Thevenize an electrical network by using the first method when in that network we have dependence. Now next we will see another example where we will use the second method, and this time also in that network we have dependent sources. Now this circuit has three resistors. We have one independent voltage source here, and we have one dependent source voltage source here, and the value of voltage value of this dependent voltage source depends on the current value which is flowing through this 2 ohm resistor. Now in the next step what we will do is we will again disconnect or remove this load resistor, because we want to find out the current value through that 4 ohm resistor. So we will remove that, and next we will measure the voltage drop across this open terminal. Now we can see that this VOC will be nothing but the summation of the voltage drop of the across this resistor and the voltage value of this voltage source. So if we can find out the voltage drop across this load resistor, that will help us to get the value of VOC. Now in this closed loop, if we apply KVL, we can easily find out the value of I1. And this time also, since we have disconnected this 4 ohm resistor and that has created this open path, so this time the value of current through this 2 ohm resistor will be different than I. So here I have taken another variable I1 to represent the current value which is flowing through this 2 ohm resistor when we don't have this 4 ohm resistor in the circuit. So if we apply KVL in this closed path, it will be minus 10, then plus 2I1. This 2I1 is the voltage drop across this resistor. Then again through this resistor 2I1 current will be flowing because we don't have any other source from where the another current will come. So this current through this 2 ohm resistor will be I1 only. So it will be 2I1 again. Then the voltage value of this dependent voltage source, which is again 2I1. So and that will be equal to 0. Now if we simplify for I1, then this equation will give us the value of I1 as 10 by 6. So 5 by 3 ampere. So VOC will be the voltage drop across this 2 ohm resistor, which will be 2 multiplied by 5 by 3 plus the voltage drop of this voltage source, which is again 2 multiplied by the current current value of I1, which is 5 by 3. So it will be 10 plus 10, 20 by 3 volt. Now next we will find out the RTH by using the second method. In that method what we do is we connect a DC voltage source between those two open terminals, and that voltage source supplies a DC current, and then we finally take the ratio of that VDC and IDC to obtain the value of Thevenin's equivalent resistance. Now we have connected this VDC here, and let's say this is supplying a current IDC in that circuit, and this time again we have deactivated all other independent sources from that circuit. So here we had a voltage source, independent voltage source, so we have shorted that path, and since we have removed that, we have deactivated that voltage source, that means the current value that will flow through this 2 ohm resistor will again change. So this time I am assuming that the current is I2, and accordingly the value of this voltage source will change, and this will be 2I2. Now this IDC current, which is supplied by this voltage source VDC, that will come after coming at this point, it will be divided into two parts. One part will flow through this, another part will flow through this. So the direction of current as per this direction of IDC will be like this. That means as per the assumption of the current that we did in the original circuit, that was from left to right through this 2 ohm resistor. But as per this circuit and as per the direction of this current value IDC, the current which is flowing through this 2 ohm resistor is from right to left. That means I2, which will be taken for this part of the simplification, this will be minus I2. So accordingly, if we take the value of this dependent voltage source, that will be minus 2I2. Now in this circuit, as we can see here, we have two separate meshes. So if we apply KVL in those two loops or meshes, we can easily find out the value of IDC or the ratio of VDC and IDC, and we can obtain the value of RTH. Now if we apply KVL here, and if we suppose start traversing that loop from this point, then it will be minus VDC, since we are traversing from minus to plus and we have taken that convention as negative, and through this 2 ohm resistor the current that will be flowing, that will be IDC minus I2. So here the voltage drop across this 2 ohm resistor will be 2, and then the current value is IDC, which is the main current supplied by this VDC, and after getting divided into two parts, I2 is flowing through this 2 ohm resistor. So what remains is IDC minus I2, and that remaining current will flow through this resistor. So it will be IDC minus I2. And then we have this voltage source whose value is 2I2, and this time it is positive terminal to negative terminal, so it will be 2I2. But as I said, the I2 now this time will be taken as minus I2, as the direction of I2 is opposite to our initial assumption, and that will be equal to 0. So if we simplify this, then it will be minus VDC plus 2IDC, and then we have minus 2I2 and here minus 2I2, so it will be 4I2, and that will be equal to 0. So this will be our one equation. And then if we apply KVL in this loop, and if we suppose start traversing from this point, then the equation that we'll be getting here is 2 for across this resistor. If the voltage drop will be again 2 multiplied by IDC minus I2, and again the voltage value of this voltage source will be 2I2, and this time I2 itself will be negative, and then the voltage drop across this 2 ohm resistor, then it will be again as per this I2 convention, it will be from positive to negative terminal, but I2 again itself is negative, so it will be minus I2. And if we follow this direction, then since current is flowing in this direction, so this will be negative, this will be positive, so that way also we will be getting minus 2I, and this will be equal to 0. So here from here what we are getting is 2IDC minus 2I2 minus 2I2 and minus 2I2, so it will be 6I2, that will be equal to 0. So that means I2, since finally we want to find out the ratio of VDC and IDC, so we have to replace I2 from both the equations. And if we take this as our second equation, then from the second equation, if we find out or if we represent I2 in terms of IDC, then it will be I2 will be equal to 2IDC by 6, that means IDC by 3. Now this relationship if we put into the first equation, then what we will be getting is minus VDC plus 2IDC minus 4, and then in place of I2 we can put IDC by 3, and that will be equal to 0. Now if we further simplify this equation and if we find out the ratio of VDC and IDC, that will be VDC by IDC, which is again equal to Thevenin's equivalent resistance for the second method, that we will get as 2 by 3 ohm. So we have found out the value of the open circuit voltage or VTH, that is 20 by 3, and we have already found out the value of Thevenin's equivalent resistance by using the second method, and that is 2 by 3 ohm. So in the final step, we will have a voltage source which will be equal to VOC or VTH, and with that we will have a resistor which will be equal to RTH, and then with that circuit we will reconnect the load resistor which we removed in the first step. So this will be R. VTH we have already obtained as 20 by 3 volt by using the normal method that we know for application of Thevenin's theorem, and that value is 20 by 3 volt. And by using the second method, we already obtained the value of Thevenin's equivalent resistance, and that value is 2 by 3 ohm. And the value of the load resistor that we disconnected in the first step, or the concerned resistor through which we want to find out the current value, that value is 4 ohm. So the current will be simply 20 by 3 divided by 2 by 3 plus 4. So finally it will be 10 by 7, and that will be 1.429 ampere. So this is the way how we can apply the second method to Theveninize an electrical network where we have dependent source. So this is the end of this class. Thank you.